Okay, so I want to talk about this little box down here. The couple of double integrals we've done so far in polar coordinates have been of this type, where the region is a fixed interval of r, a fixed interval of theta. And when I say fixed interval, I mean that the endpoints are constants. That's been the case so far, but kind of like in 15.2, we've seen that a lot of regions are more complicated than that, at least as far as rectangular coordinates are concerned, where we have regions that are bounded by functions of x or functions of y. The same thing can happen in polar coordinates as well. Sometimes we're looking for a region that's bounded by two polar functions. And polar functions typically are given where r as a function of theta. And so we really only consider that type here. There's not a type 1 and a type 2 that we bother with. It's just we treat r as a function of theta in these cases. So if you have a continuous function f on a polar region of that form, notice theta has a fixed interval, but r lies between two functions of theta, then we could do something similar to what we did with the double integrals over general regions, type 1 regions or type 2 regions in 15.2. Where basically once you convert your rectangular form into polar form, the only difference is that these limits of integration are using functions of theta instead of constants. So I want to do an example where we have to use that. Okay. All right, so here we're finding the area of a region inside a cardioid, r equals 1 plus cosine of theta, and outside of a circle, r equals 3 cosine of theta. Back in trigonometry, you learn how to graph polar functions of these types, and you probably reviewed that in Calculus 2. In fact, in Calculus 2, you're taught how to do this exact problem. But what we want to do is take an alternative approach using double integrals. So the first thing that we need to do is figure out what this region looks like, and we're going to graph it. And again, you kind of have to remember how graphs of polar functions work. So the cardioid, 1 plus cosine of theta, it's going to have intercepts on my vertical axis at 1 and -1. It's going to have a intercept here at 2 on the polar axis, or positive x-axis if you prefer. And remember, cardioids, as the name implies, take on this sort of heart shape, which I'm not drawing very well, but that's all right. The circle, 3 cosine of theta, has a point at the pole, and it's going to open horizontally to the right away and have a diameter of 3. So it's going to go out to 3. That would mean its radius is 1.5. That's going to put it roughly here and here. Whoops, I put that in the wrong place. Here and here. Ignore those points there. Okay, so it's going to be, and this is an absolutely terrible circle. So feel free to laugh at my attempt to sketch a circle. All right, so the description says we're looking for the region inside the cardioid and outside the circle. That's this region right here. Okay, now we want to use the symmetry to our advantage, kind of like the previous examples. So if I were to just find the area of this region right here, I could double it to get the total area between those two parts. What I'm going to do is sort of just zoom in on this region right here. So I'm going to go in a little further. Okay, and we've got this part of the cardioid kind of going off this direction, and then we have this circle that goes off this direction. And this here is the region I want to find the area of. So in order to do that, it's going to be important that we know where these 2 points intersect. I want to associate that with a particular value of theta. So just like anytime you're looking for an intersection of two curves, we set the functions equal to each other. My cardioid was 1 plus cosine of theta, and my circle was 3 cosine of theta. This leads to cosine of theta equals 1/2, giving me two solutions within one revolution of the unit circle. So theta could either equal pi over 3 or 5 pi over 3. Okay. We're going to use pi over 3 because that corresponds to this intercept. 5 pi over 3 would correspond to this one, but we're only going to worry about this part right here. So this, I don't care what the actual coordinates of that point are. What matters is that I get to that point when theta is equal to pi over 3. And you can check that by plugging pi over 3 into each of these functions. Now this region I'm actually going to split into 2 parts. I'm going to call this one R1, everything to the right of the y-axis, and then everything to the left of that y-axis is R2. By the way, in polar coordinates, we technically don't call this the y-axis. It's called the line theta equals pi over 2. I don't really care about making that distinction right now. So here's the tricky thing. And again, my drawing is not very good, so it's kind of hindering this explanation. I might fix my circle a little bit, make it a little rounder, I guess. Okay. So if I wanted to figure out how to describe this region as a set, R1 in particular, I need to figure out what the bounds are on my R, my radius, or the R for my polar coordinates. Now, notice I can't just say that R goes from 0 to this function out here, because if I were to try and say pick a point here and draw a straight line from the pole to that point, and again my picture is not great, so it's kind of hard to see this. Some of the points on that little line are going to be outside of the region R1. In fact, it's only after I break out of that circle right around there that I get back into points that are in the region R1. So in this sense, we're only looking for values of R that are greater than the circle 3 cosine of theta and less than the cardioid 1 plus cosine of theta. That means R1 can be described by this region. It's the set of all R theta such that R lies between, again, the circle 3 cosine of theta and the cardioid 1 plus cosine of theta. Okay, how do we describe the interval for theta in this example? Where again, going back to this, R1, we know when theta is equal to pi over 3, that takes us to this intercept right here. And if I kind of follow this point along the cardioid as theta increases, when I get to theta equals pi over 2, I'm now at this intercept. And again, you can check that by plugging pi over 2 into the equation for your cardioid to see that we get this point in polar coordinates. So, I wrote pi over 3. I should have written pi over 2. Pi over 2. So that means the interval for my theta is pi over 3 to pi over 2. Okay? That's R1. R2, how do we describe R2? Well, let's go back up here. R2, you'll notice, is completely separate from that circle. The circle is to the right of my y-axis. R2 is completely to the left. So R2 has no dependence on that circle. It's only bounded by the cardioid. So for R2, if I want to describe R2 as a set, it's the set of all R theta such that, looking at the picture, notice R, if I draw any line segment from the pole to any point out here, the line's completely contained in that region R2. So all of the points are going to have values of R that are somewhere between 0 and 1 plus cosine of theta. That's the function that I'm using for R1. So 0, R, 1 plus cosine of theta. Okay. And this time, as I go from theta equals pi over 2 all the way to this point occurs when theta is equal to pi. So my interval for theta now looks like pi over 2 to pi. Okay. Now, using one of those properties, if you notice, the region that I'm looking for the area under, or the area for, is the union of these two regions here, and we had that property I want to say it was 15.2, which says that to evaluate the double integral, the double integral of a union of two regions, we can just do the two regions separately and add those. So what I'm going to do is find the area of R1 and then find the area of R2 and then add those up to get the area of this region, double that answer to get the area of the entire region. So let's start with the area for region 1. So that's defined to be the double integral over region 1 of dA. Remember, that was one of those properties. The double integral over region dA gives us the area of that region. But if we're using polar coordinates, I have to convert that. So again, using R1, just as a reminder, these are my intervals here. Theta is going to be on the outside, pi over 3 to pi over 2, and here's what I'm using for R. So theta goes from pi over 3 to pi over 2. R goes from 3 cosine of theta to 1 plus cosine of theta. And then dA, remember, becomes R dr d theta. Okay? Now in this case, I can't think of this as a product of a function of r and a function of theta and use that to pull the d theta out, because that only works when we're talking about regions where these two pairs of limits of integrations are constants. Because these are functions, I can't actually do that here, but that's all right. The integral here, integrating with respect to r first, I'd get an r squared over 2. Let's treat that as a 1/2 and pull it all the way out. That's fine to do. Pi over 3, pi over 2 of r squared from 3 cosine of theta, 1 plus cosine of theta, d theta. Okay? 1/2 pi over 3 to pi over 2. All right. Now, plugging this in, 1 plus cosine quantity squared minus 3 cosines theta, all quantity squared, comes out to this after simplifying, 1 minus 2 cosine of theta minus 8 cosine squared of theta d theta. All right? Here's where you need to remember how you deal with trigonometric integrals from calculus 2. You have this cosine squared here. We can use a power reduction formula to reduce the size of this. Remember, cosine squared of theta is equal to 1/2 times 1 plus cosine of 2 theta. So if I made that substitution and did a bunch of simplifying, all of this will eventually reduce down to this. 1/2 times the integral from pi over 3 to pi over 2 of, this turns into negative 3 plus 2 cosine, this should be a plus right here, plus 2 cosine of theta, minus 4 cosine of 2 theta, d theta. So in the interest of time, I'm not going to go through all the steps of evaluating this. This is a more basic integral to do. So what this eventually will come out to after some work is 1 minus pi over 4. Okay? That's the area of region 1. Area of region 2 is similar. We're looking for a double integral over region 2 of dA, which becomes, and remember, here's how I described R2, region 2, the integral from pi over 2 to pi, integral from 0 to 1 plus cosine of theta, r dr d theta. Again, the integral of r with respect to r is r squared over 2, but it's kind of convenient to pull that 1/2 out, giving us this. Then I have r squared from 0 to 1 plus cosine of theta, d theta. This is equal to 1/2 times the integral from pi over 2 to pi. If I squared that, I'm going to get 1 plus 2 cosine of theta plus cosine squared of theta d theta. All right, and again, very similar to the previous integral. If I wanted to evaluate that, I'm going to need to use a reduction formula here. But again, sort of skipping the steps just to save some time. What this integral ends up coming out to is, let's see, it was -1 plus 3 pi over 8. Okay, so to wrap it up, the area of the region that we care about is double the combined areas that we just found. So if I come down here, I can write that as 2 times the area of region 1 plus the area of region 2. That's 2 times region 1 was 1 minus pi over 4. That's the area that we found. Plus this right here, which is -1 plus 3 pi over 8. Working that out completely gives us pi over 4. Okay? All right.